Hello and welcome. In this video, I'll be covering section 2.1, which is over the derivative and the slope of a graph. My goal for you by the end of the video is to be able to identify tangent lines to a graph at a point, to be able to approximate the slopes of tangent lines to graphs at points, to be able to use the limit definition to find the slopes of graphs at points, as well as to find the derivatives of functions, and to be able to describe the relationship between differentiability and continuity. So first, let's review what a tangent line is for a graph. So recall, a tangent line is essentially a line that would just touch the graph at a single point and then also have the exact same slope at that point. So if I went over here on the left side here and just drew an example of a tangent line, remember that's something that just essentially grazes off of the graph at each of those points. So if I did another one here at this high point, notice it again doesn't necessarily cross in more than one place. That one, if I did extend it out, it would technically cross again over in this region, but again, it's not a tangent line at that point. It's a tangent line over in this area right here. So this is where the tangent line is. It is not over in the other area. So this area right here is definitely not. So what can we do with this info? Well, we can also talk about what secant lines are, and eventually we're going to utilize secant lines to be able to come up with what a slope of a tangent line happens to be. So a secant line, if you remember, is a line that crosses a graph through 2 points. So if I just use these 2 points over here on the right, notice that's definitely not a tangent, because the tangent would have been like somewhere right about there if I wanted it to be parallel. So with this one, if I end up getting those 2 points closer and closer and closer, notice that would start turning into what looks a lot more like a tangent line. So let's go ahead and review the concept of slope. So remember, slope was that formula y2 minus y1 over x2 minus x1. And if we actually had a point that was just x and then whatever the function is at x, so x comma f of x, and then we had a second point that was just horizontally a change in x or delta x away from that point, notice that would then turn into this format where it would be x plus delta x is the x coordinate, and then the function at x plus delta x as the y coordinate. So if I were to utilize this slope formula with a y2 minus y1, that would be essentially just taking the y from the second point, subtracting the y from the first point, and that would create this f of x plus delta x minus f of x. And then I would take the two x values, x plus delta x, and subtract x. But on the bottom, what's kind of nice about that is those two x values would actually cancel out, because x minus x would be 0, so all it would leave on the bottom is that delta x. So if you remember, this was the thing that we called the difference quotient, but all of this right here is essentially just a shortcut for coming up with the slope of a secant line. So I'll try and use this visual to help you guys kind of see exactly what's going on. So notice we have an x delta x that's down here for our change in x, and then we have our change in y, delta y, that goes vertically, and then we have our ordered pair up here that is that x plus delta x idea. It's just using h as an easier variable to actually type in. So if we think in terms of what does this allow me to do, well, as you can see, there's the tangent line that's right here, and then there's the secant line that's actually connecting those two right there. So the closer I bring those 2 points together, so if I change what that delta x is, right now it's a distance of 2 horizontally, but as I change that and make it get closer and closer, notice that the graph itself of that secant line starts looking a lot more like a tangent line. And once I get really, really close to, like, say 0, where I would not be adding really much at all, notice those 2 points are really close, that now when I get to where it's actually equal to 0, it truly is that tangent line. And if I continue to go in the other direction, notice it turns right back into a secant line. So again, the moral of the story here is, if you kind of think ahead, what we're going to be doing is trying to find equations of tangent lines at a single point, or finding a slope of a graph at a single point instead of having to use the slope formula. So hopefully that visual will help you make some sense of what we're going to slowly start getting into, which is this idea of finding the slope, but using something that we've learned recently, which is called the limit process. So if we wanted to find the exact slope of a tangent line, but only at a single point instead of needing or requiring 2 points to come up with a slope, what we'll do is we'll essentially just find the difference quotient and then make the limit as delta x approaches 0 happen. And that would actually give us the slope of our tangent line. Now, it's not always going to be a limit that we can evaluate. In other words, there's going to be some situations where I cannot have a slope. One example being a vertical line. Remember, the slope we use undefined to describe it. With each one of these, notice if you don't like the delta x symbol, in other words, you don't like having to do math with that delta x, by all means, you can also just substitute in a letter such as h. It's a very common one in a lot of books. And just make your limit as h approaches 0. So you can really just substitute in place of these delta x's with whatever variable you would like, so long as it's not just x itself. So let's go ahead and try an example of this. So notice this problem just wants us to find the slope of the graph on f of x equaling x squared, specifically at the point 2, 4. So what we'll do is we'll go ahead and set up our limit. So it's going to be the limit as, I'm going to go ahead and use h just to make things a little bit easier to read here. So it's going to be the limit as h approaches 0 of, and then on top it would be the f of x plus h minus f of x, and then all over h. So that's my setup. And now my function that I'm going to actually plug things into is this f of x equaling x squared. So now it would turn into, when I do that substitution, that x plus h would be squared. Then I would subtract f of x, which is x squared, and then still all over h. So now I need to expand out the numerator and try and combine as many like terms as possible. So I still have the limit as h approaches 0 of, this would become x squared plus 2xh plus h squared, then minus x squared, still all over h. At this point, hopefully we can see that there's some terms that are going to be able to cancel out. We have x squared will be able to cancel with negative x squared. And now at this point we can factor out the h from the numerator. So it would now be the limit as h approaches 0 of h times, and then 2x plus h would be left if I factored that h out. And what's nice now is those h values can divide to equal 1. And then now I can go ahead and try and apply this limit as h is going to 0. Plug that in, and that would give me 2x. So since this is only an x, and this is really my slope equation, remember all of this was equal to m. So if I just said that is my equation for my slope, all I need now is to plug in the x value from the point. So at 2, 4, my slope is going to equal 2 times the x value, which is 2, which happens to be 4. So my slope at 2, 4 on the graph of x squared has a value of 4. So let's go ahead and do another example. This one's going to be now finding a specific formula. So instead of actually finding the slope at a specific point, now it wants a formula, and then I'm going to find the slope at 2 separate points. And this one's a little bit more intense than just the plain x squared, but remember this is going to be the limit as h approaches 0 of my difference quotient. So I'm going to go ahead and just plug in the x plus h to the function. So it would be 3 x plus h quantity squared plus 1, then minus the f of x function, so 3x squared plus 1. And since there's more than one term, I'll throw a parenthesis grouping to remind me about that minus being needed to, I guess, be distributed through. And then it's still all over h. So now at this point, we'll go ahead and expand out the numerator. Still have my limit as h is approaching 0. And then I've got 3 that's going to be multiplying with x squared plus 2xh plus h squared. Still have the plus 1, and I'll go ahead and distribute that negative through, so I get a negative 3x squared and a negative 1 all over h. So now I just need to distribute that 3 through, so I get the limit as h approaches 0 still of 3x squared plus 6xh plus 3h squared plus 1 minus 3x squared minus 1 all over h. So I do have a 3x squared and a negative 3x squared that we're going to be able to reduce down to a 0. I have a positive 1 and a negative 1 that reduce down to a 0. And every term that's left, notice, has a h involved, so I can go ahead and say that the limit as h approaches 0 of this, if I factor the h out in the numerator, that would leave 6x, then plus 3h all over h. By doing that factoring, that h that came out will reduce with the h that's on the bottom. And now again I can make all of my h's equal 0, just try the direct substitution, and I get that 6x, it didn't show up very well, 6x is my slope formula. So that would be my m. So again, pretty similar to what we did before, it's just the wording of the question is slightly different. It actually wanted this formula. Now it's go ahead and use it to come up with a slope at each of these points. So at 1, 4, if I go ahead and plug into my slope formula, it would be 6 times the x value, which is 1, which happens to equal 6. At the point negative 2, 13 on the graph, the rate of my graph changing, or the slope of that, would be 6 times negative 2, which would equal negative 12. And if we think about the shape of this graph, it would just be a parabola shifted up 1 and pretty narrow because it's been stretched vertically by a factor of 3. The fact that negative 2, 13, which would be probably somewhere way up here, having a really steep negative line, hopefully seems reasonable. So at least those two answers make sense in relation to the picture of how steep the graph actually was right there. So those two examples lead us towards a very, very big topic in a calculus class, which is this idea of a derivative. So a derivative is essentially what we just found before, where if I do the limit process of that difference quotient, it's giving me a slope formula, but essentially what that slope formula is its special name is actually, it's called a derivative. And the notation for each of these can be all sorts of different options, so I've kind of put most of the common ones on this screen for you to be able to see, as well as how you say it out loud. So the first one, f prime of x. The second one is the derivative of y with respect to x. Usually we also can just say dy dx for that one. The one in the middle, y prime. Again, all of these are just representing a way that we could say or notate that we have a derivative involved. The next one, d over dx of f of x. So it's, if we say it out, it's the derivative with respect to x of f of x. So the whole with respect to that each of these has had, respect to x, that just tells us which variable would be like our input variable or the independent variable. And then the last one is a lot less common in I guess our book, but potentially you might see it from time to time, is the d subscript x and then of y. That again just represents the derivative with respect to x of y. Now in regard to all of the different notations, a problem as you're working through it will kind of lend the which one of those versions would you want to use most. It would kind of show itself as you were working. So for example, if you were working with functions, you'll probably do the like f prime of x like you can see on this screen. If you were dealing with x's and y's, you could go in between saying like the y prime, or sometimes dy over dx makes more sense. But really when it's all said and done, as long as you are notating it in some way, shape, or form using one of those examples from the previous slide, it's all good. It's just a matter of usually as you work through a problem, you can kind of tell which one is the one that makes the most sense for that situation. So anyway, going back to this concept, a derivative really is just a slope equation for a tangent line, and really just gives us the ability to represent the slope at a single point as opposed to being required to have 2 points. What we can do is actually modify that slope equation that we had from before and just substitute this f prime of x in its place. So instead of having m equals like it was before, we could actually use this function notation, or this derivative function notation, of f prime of x equaling, and notice it's still the limit as delta x approaches 0 of that difference quotient. So a function is called differentiable. That's one of the key words that you're going to hear from time to time, at that specific value x, so long as its derivative exists. So in other words, if you get a derivative that doesn't exist, then that means it's not differentiable at that value. This whole process of finding derivatives, you're going to have this show up quite often, as it's called differentiation. So if you ever see some question that involves that word differentiation, that just is your key to recognizing that you're going to need to take a derivative. It's important to note, I guess, that derivatives don't have to use the variable x. In other words, you can have different variables. So like in some contexts, having a function in relation to time, having t as a variable that's like my independent variable, is something that we still can do. It's just when we find our derivative, it would be with respect to t instead of saying with respect to x. So notice, as far as the notations are concerned from the previous slide, you would just have a small modification, but the thing to kind of take account is whatever is in the denominator, this dt, that's really just telling you what you're doing a derivative with respect to. The other parts are what you're actually taking a derivative of. So like dy over dt is you're taking the derivative of some y equation with respect to that t variable. So the t would be the thing that you would actually follow through with all of the rules that we're going to be learning throughout this entire chapter. Today, or this video, is really just an intro into what the concept of a derivative really is. And if you can just get it down that derivative represents slope, you're going to find that you're going to have a pretty better, or a better understanding of what we were going to need to accomplish moving forward. But we will have different applications of why would we care what the slope is as the chapter kind of comes to an end. So there will be some application things later. So hold on to those why do I need to know this type questions until we get to there. Now let's go ahead and try an example that's just simply saying find the derivative of this function. So again, it is in function notation, so I'll probably go ahead and utilize the f prime notation for it. So f prime of x is going to be equivalent to that limit as h approaches 0 of this 2x plus h quantity squared minus 3 times x plus h, then minus the original function x, or 2x squared minus 3x. And then all of that being divided by h. So now I'll go ahead and do what I've done on the previous ones, just expand out the numerator, see how many like terms I can combine. So this will turn into a 2x squared plus 2xh plus h squared, then minus 3x minus 3h if I distribute that negative 3 through that parenthesis, and then a minus 2x squared, and now a plus 3x if I distribute that negative through the last parenthesis. And so now it will just turn into, let's go ahead and distribute the 2 through. And so this would now turn into 2x squared plus 4xh plus 2h squared minus 3x minus 3h minus 2x squared plus 3x, still all over h. So now it's to a point where all the parentheses are gone, so it should be able to start canceling things out. Looks like I have a positive 2x squared and a negative 2x squared that can cancel. I have a negative 3x that will cancel with a positive 3x, and then all the terms that are left have an h that I could factor out of them. That's nice because I want to be able to try and cancel this h that's on the bottom as well. So if I take the h out of those terms, it would leave 4x, then plus 2h, then minus 3. And now that I'm at this point, the h terms that I have dividing would be able to turn into a 1. And now if I let all of the h's equal 0, there's only one of them, I can now write what this would finally turn into, which is, actually I'll go ahead and go vertically here, because the notation still is going to be this f prime of x is equal to, and then for this one it would be 4x take away 3, because this h that's on the 2 is turning into 0, and 2 times 0 would go away. So my derivative for this function 2x squared minus 3x would turn into this f prime of x equaling 4x minus 3. Now again, the application of why we would care to find a derivative is going to eventually show itself. So right now, just think of it as we're building a skill that eventually later will have an application that will actually see why we're doing what we're doing. But for right now, like I said multiple times so far, if you can just make a connection that derivative and slope go together, the easier things are going to be as we transition it into those newer topics. Now this is the last thing to talk about in this video, so we're almost done. This one is now talking about differentiability, which is just an interesting word to say, as well as continuity. So it's important to note that not every function actually is differentiable. In other words, it's not always something where you can take a derivative of something. So the examples that are here are just a few types of graphs. It's not every type of graph that doesn't have a derivative, but one place or one time when you don't have a derivative would be anytime you have like a vertical tangent line. So like right here in the middle of this, I think this would have been like the, what is that one? The cube root of x, it looks like. But that one has a vertical tangent line like right at the origin. So if I think in terms of what's the slope of that line, well, it's vertical, so I would actually say that the slope is undefined, hence why it's not differentiable. The next type would be like this discontinuity idea, so where it like maybe ends right here and then picks up at the top here. So anytime you have that, I can't really draw a tangent line at those open circle areas, or I can draw a whole bunch of different tangent lines that touch it only at that one spot, but that would be a situation where it's not differentiable right there. Anytime you have a cusp, which is essentially just like a sharp edge, so in this case it's the sharp edge there at the origin, that one would also not have a derivative at that specific point, but it would be differentiable everywhere else, it looks like. And then the last one, the absolute value graph, where it has like a vertex or what we call a node. Again, it's just another sharp edge. Difference between a node and a cusp is a cusp, it's curving coming in, whereas a node, it's two linear things meeting and forming that point. But what we can learn from this, and what the application of why we would care about things that are differentiable or not differentiable, is if I actually know that something is differentiable at some specific number, what we can actually confirm for ourselves is it actually has to be continuous at that specific value. So notice we can kind of get away from having to do the idea of the limit and use that to come up with, is this continuous, yes or no? We can actually just say, if I can find a derivative at that number, then I can guarantee for myself that it truly is continuous at that value. So hopefully this video has been helpful. I know the problems in the homework are going to be a little bit more time consuming because it uses that difference quotient over and over and over. But hang in there, get through it. And if you have questions, by all means reach out, let me know, and I'll do whatever I can to make it make sense. Appreciate you taking the time watching the video, and we'll catch you next time.